So let's begin with this problem, which is titled Permutation in String. You are given two strings, S1 and S2, and you want to write a function to determine if S2 contains some permutation of S1. In other words, if any of S1's permutations is a substring of S2, then you need to return a true. Otherwise, you return a false. Since we return either a true or false in this problem, it's clearly a decision problem. Recall that a decision problem is a problem whose output is a Boolean value, either true or false. So let's look at the two examples given here. In the first example, S1 is the string AB and S2 is this longer string. And the question is whether any of the permutations of S1 appears in S2. So this means either the string AB or the string BA needs to appear in S2 in order for us to return a true. So by visual examination here, you can see that the string BA appears in S2, because of which the output is going to be a true, since one of the permutations of S1 was found to be a substring of S2. In the second example, S1 is the same string, but S2 is the string EIDBOAOO. So between B and A here, we have an extra O. And the presence of this extra character prevents BA from becoming a substring of S2. So neither AB appears in S2 nor BA appears in S2, and so the output is supposed to be a false. It is given to us that the two strings S1 and S2 are only going to contain the lowercase letters, that is the 26 letters from small a through small z, and the string lengths can be relatively large. So obviously, for us to return a true in this problem, that is for any of S1's permutations to be a substring of S2, the length of S1 has to be less than or equal to the length of S2. Only then will it be possible for a permutation of S1 to exist as a substring of S2. But we haven't been told that S1 is guaranteed to be no more in length than S2. So we have to be prepared for the possibility that we could be given two strings where the first string is longer than the second. So I would like you to take a few minutes to think about this yourself. Pause this video and hit play when you are ready to continue. Now we can think of a very naive, brute force, exhaustive way of doing this, which is to generate all possible permutations of S1 using techniques that you might have studied in the combinatorial enumeration section of the course, and then taking each of those permutations, we could check whether any of them appears as a substring of S2 or not. That's too expensive, so we are not even going to consider that as an option here. Our solution needs to run way faster than that. So as before, we are going to adopt a decrease and conquer approach, putting on the hat of a lazy manager, and we are going to ask ourselves, as a lazy manager, suppose I focused only on the last character of S2, which is the longer string. If I focused only on the last character of S2 and I asked the question, how could this last character be involved in a valid solution? Or could this last character be involved in a valid solution, which means could there be a permutation of S1 which ends at my character? If so, the answer for the overall problem would be a true. If not, at least the local answer to my subproblem is a false. So if any other manager in the corporate hierarchy found a permutation of S1 ending at their respective index, then the answer would be a true. So in general, any lazy manager is going to be focused on, let's say, index I of S2. So I might be focused on the last character of S2, which is, let's say, the n minus first character, assuming that n is the length of S2. But from the perspective of an arbitrary worker in the corporate hierarchy, an arbitrary worker, an arbitrary manager would be focused on index I within the string S2 and will want to know if there is a permutation of S1 that ends at index I. And instead of trying to check this exhaustively by looking at every single character of S1, being lazy, we would want to ask the question, could we rely on the work that our immediate subordinate has done? So our immediate subordinate would have looked at the subproblem delineated by the yellow rectangle and would have asked the question, is there a permutation of S1 which ends at let's say index I minus 1. So they would have looked at all the characters in this shaded region which are common to their subproblem and also to my subproblem. The difference between my subordinate subproblem and my subproblem is that this particular character is going to be discarded from my subordinate subproblem, and this particular character is new to my subproblem. But notice that the size of the subproblem is the same. It is essentially the length of the string S1. Right? So the size of any subproblem, any lazy manager's subproblem, is going to be equal to the length of S1, because we want to check if there is any permutation of S1 ending at the last character, which is the character that the manager is focused on. So because the size of any subproblem is fixed, this is an example of a fixed length sliding window problem, because when we move from one lazy manager to his or her immediate boss, the length of the subproblem remains the same. What happens is that the subproblem, which you can think of as a window here, slides by one place to the right, keeping its length, preserving its length. So coming back to my subproblem, what I want to know from my subordinate is there a useful summary of this shaded yellow part of my subordinate's subproblem which I could reuse for my subproblem? That is, I want to know if there are, if all the characters in this yellow shaded region happen to be drawn from the string S1. If so, and if the last character here happens to be, the sole missing character from S1, then I would be completing an entire permutation of S1. So I want to figure out from my subordinate, I want my subordinate to tell me how many of these characters are drawn from S1. Since we are okay with any permutation of S1, the order in which the characters of S1 appear don't matter. What matters is that taken as a whole, this green rectangle has to be filled exactly with the characters of S1. So it's natural, therefore, to think of a summary of these characters as being stored in a frequency table of some kind. In other words, a hash table which is storing the frequency with which different characters appear within this yellow shaded region. And so I would take that hash table, and that hash table would presumably also contain this single character on the left end. I would remove this character from that hash table. I would add my own character to it, and then I would compare the set of characters in the hash table with the set of characters of S1, and if those two sets happen to match exactly, then I know that the characters making up my subproblem are essentially a permutation of S1. So I'm going to follow the same template that I followed in the first session. So this is a fixed length sliding window problem, and the length of the sliding window is basically the length of S1, right? So this is the K value, where K was the length of the fixed length sliding window. That's going to be length of S1. And so as a lazy manager, what I would be doing, or any lazy manager would be doing, is varying this index I from K to n minus 1, right, where n here is the length of S2. So any lazy manager whose subproblem ends at index I is going to take the hash table inherited from the subordinate and kick out the leftmost element. Kick out the leftmost element which was part of the subordinate's subproblem, and that, remember, was at index n minus k, sorry, I minus k, and add. So this has to be kicked out and this element has to be added. Now kicking out I minus k from the hash table can be done without checking if that character exists in the hash table, because it obviously must exist already, since my subordinate presumably did his or her job correctly. So I can just take, let's say hmap is the hash table, I can just remove the frequency or reduce the frequency of this character in the hash table by 1. So which character is this? Well, it's the character at index I minus k within the string S2. So S2 of I minus k is the key, and the value in the hash table is its frequency. So I will subtract this, I will reduce this by 1, and if by reducing it by 1 it becomes the frequency now becomes 0, that means this particular character, whatever that character is no longer found within, you know, this subarray or substring. We basically delete it from the hash table. So delete that key from the hash table, since we only want to store characters that have a non-zero frequency. And so this part deals with kicking out the leftmost character, and now we have to add the rightmost character. So if the rightmost character, which is S2 of I, if the rightmost character already exists in the hash map, then we just have to increase its frequency by 1. So hmap of S2 of I has to be increased by 1. Otherwise, if it doesn't exist in the hash table, we have to add it to the hash table with a frequency value of 1. So what we have done here is added the rightmost element, and now our hash table is updated. Our frequency table inherited from our subordinate has been updated, and what we need to check now is whether this frequency table exactly matches the frequency table of the string S1. Now the frequency table of the string S1 should have been created in the initialization phase of our code. So I'm going to assume that it's already been done here, and let's say that the variable for it is hmap underscore s1. So hmap underscore s1 is essentially populated with the frequency of every character within the string s1, and that means when we begin we would have iterated over every character of s1 and added it to this hash table. So if the current character we are looking at, let me say if s1 of I, current character we are looking at, is in the hash table already, hmap underscore s1, then we will add a 1 to its frequency value. Otherwise we just set its frequency value to be equal to 1. So that populates our hmap underscore s1, our frequency table for the string s1. And what we have to do here is to compare these two frequency tables. That is, if hmap underscore s1 happens to be identical to our frequency table for s2, I could have called that as hmap underscore s2, but since I just called it as hmap, I'm just going to leave it like that. If these two hash tables are the same, that means this substring exactly contains all the characters of the string s1. That means this substring is a permutation of s1, and in that case, since this is a decision problem, we can immediately return a true, since we know what the final answer is. And if the two don't match, then we just keep continuing, since we don't know, maybe some other manager might find that the substring ending at their character matches a permutation of s1. So we wait until all the managers have done their work, and if we didn't return true from any of them, then finally we would know that none of the substrings ending at the different indices corresponded to a permutation of s1, and so we return a false at that stage. Now what I have done here is I have assumed that we have written the code for a general manager in the hierarchy, but we haven't written the code yet for the leftmost window. Remember that we have in our initialization phase, we have to look at the leftmost window of our overall problem, and the leftmost window is going to span the indices from 0 to the length of s1 minus 1, right? Or you can say k minus 1, where k is the length of s1. So this window must be looked at, and the characters in it should be used to populate our hash map. So let's just fill that in. Our hash map here is going to be initialized to an empty dictionary, and then as we iterate over all the characters from index 0 through, let's say, k minus 1, where k is the length of s1. I'm just using the variable k because we've used that in earlier problems. So if s2 of I, if the character happens to be in the hash map already, we just increment its frequency by 1, Otherwise, we set its frequency to be equal to 1. Okay, so this initializes our leftmost window, and so we need to add that check here also, that what if the leftmost window happened to correspond to a permutation of the string S1. If it did, then we would return a true then and there as part of the initialization phase itself. Otherwise, we start looking at the work being done by the managers up the chain. So in some sense, the leftmost window is being initialized by the bottommost manager. If you like, you could even think of this work as being done by a leaf node. All the work to initialize the leftmost window, and then the managers take over. So it's possible that the leaf level worker itself might find that the leftmost window corresponds to a permutation of S1, in which case we should return a true there. Otherwise, we would let our internal nodes, our managers, figure out the answer. So let me record the fact that, just in case you're wondering here, this is the initialization part. Normally, I think in the first session I had the initialization part entirely in green. Here I have a mixture of white and green. And then the red part is the actual loop, the work being done by the managers. So what's the time complexity of this algorithm? So clearly, in order to build the frequency table of the smaller string, right, S1 is generally the smaller string, although it doesn't have to be that. This is going to be equal to, let's say, the length of the string S1. This is also going to take time proportional to the length of the string S1, because that is the size of our window, including the initial window. And then the for loop is going to run over the remaining S2 minus S1 characters roughly. So for each of these characters, we are adjusting the hash table, the hash map for the frequency table for S2. That takes a constant amount of time, and then we are checking here whether the two hash tables match. So this check is going to compare the keys in both hash tables to see if they are identical or not. Since we know that there are only 26 possible keys, since the keys can only be lowercase letters, it's basically a constant time operation. So the whole thing here is going to take time order, say the length of S2 minus the length of S1. This took time proportional to the length of S1, and so the overall time for this procedure is going to be roughly the length of S1 plus the length of S2, right? Looking at all the characters of S1 to create the initial hash map, and then looking at all the characters of S2, not just to create the initial hash map, but also to as we are iterating through this for loop. So that's the time complexity. The space complexity is constant, since we have both frequency tables having at most 26 keys. So the total space taken by them would be roughly a constant. Now there is one special optimization you can do for this problem. I don't think it's absolutely required, but if you wanted, you could build the frequency table in a way that this comparison between the two hash maps, instead of comparing potentially 26 keys, you could do this comparison instantly. And the idea there is, instead of storing two separate frequency tables and then matching the frequency values, if we stored, say, just the difference of the two frequency tables, that is, if we stored this minus this in a single hash map, right? So that means when we initialize our hash map here, we do exactly what we've done here, but then our second hash map is essentially identical to the first, but as we are parsing the characters of S2 in the leftmost window, we start subtracting the frequencies of these characters from the frequency tables here. So it's possible that there are some characters here which don't appear here, so their frequencies won't change. There could be some characters here which don't appear there, so when we subtract the frequencies, the resulting frequency for those characters might end up being negative. But characters which have the same frequency in both these tables, their frequency would be exactly 0. And what we can decide to do is, characters with a frequency of 0 are not going to be stored in the hash map. So what we are storing in our single hash map is just, the difference between the frequencies of two characters which happen to either be positive or negative, but not 0. And that allows us to come to this point and to say that if instead of saying that the two hash tables are the same, we're going to look at the single hash table, and if the frequency value here for every single character is a 0, that means the hash table is essentially empty, because whenever there is a matching character, we reduce its frequency in the hash table, since we are only storing the difference of the two frequencies. And so if there is a permutation of S1 which is a substring of S2, there'll come a point when the difference table, right, the difference of the frequencies table, that table will have all frequencies being exactly equal to 0, which means none of those keys will exist in the hash table, which means this check will just be a check for whether the hash table is empty or not. If it is empty, then we return a true, otherwise we return a false at the very end. So this is just a small trick to optimize things to make them run a little faster, but since this is not something we can do for most problems, I'm not going to emphasize it too much here.